And what are we trying to capture here? There's a couple of things I want to emphasize with you. The first thing I want to say is that when we talk about the position function, we write it in a couple different ways. The first way is S of t like this. And the second way is ds dt like this. And what we want to do, these symbols are going to have meaning for us. So this top letter here, this is the dependent variable. And this bottom one here is the independent variable. And that's the same for this guy. When you look at the function notation, the independent variable is the thing inside the parentheses, and the dependent one is the one that's outside, right? So why do I bring this up yet again? I mean, I talk about this all the time. Well, in section 2.7, we're going to start looking at rates of change of different types of things. It's not always time. It could be with respect to some other variable. So I'm just emphasizing this idea again, like what depends on what. And we know that we can transition to velocity. And the way that you transition from velocity, which would be v of t, or I put this too soon. This has to go down lower. The derivative is the velocity, right? So this is just s. I mean, there is no Leibniz notation when you're not taking a derivative. Okay. So I guess one of the things that was mentioned in the video that's a little bit new is, velocity. When we're in 5A right now, our object has linear motion. So really, we're talking about linear motion. And the word linear means line. So you'll see a lot of problems that say the object is moving along a coordinate axis. And for us, that means it's either moving left, right, or up, down. So when you think about the linear motion, you're thinking about an object moving along a coordinate axis. So it could be left, right, or it could be up, down. So we're not going to be working with two-dimensional curves or anything. We do have curves, but that's not the type of motion that we're describing. So when I talk about motion, it's just an object moving in a straight line. Okay. So, and I'm going to make this idea clearer in our examples today. Now, one of the new ideas that we saw was that this velocity has direction. And the direction is either left, right, or up, down. Okay. But what I can do with the velocity is I can remove the direction component. So if I take absolute value of v of t, this removes the direction. And now we have speed. So speed is simply the absolute value of the velocity. So I can't remember. Did we talk about that movie Baby Driver in this class? I don't know. It's this movie starring that guy, that young guy. Forgot his name, Ansel. His name Ansel something. Anyways, in the movie, the movie opens with a chase scene, and he's driving in reverse for like a long time. And when he's driving in reverse, the velocity is going to be negative. But the speed is just going to be however fast he's going. The speed, it doesn't matter if you're going forwards or you're going backwards. It's just whatever the speedometer says. Okay. So that's the difference. Okay. And then, of course, you guys know that the way that we go from one to the other is we differentiate with respect to the independent variable. So we've talked about this a zillion times. You're like, why does he keep talking about this? And I'm sorry. I need to. So just as a reminder, if you have d dt, that's the differentiation operator, and then you apply that to the first derivative, that's how you get the second derivative like this. So it's almost like the d and the d get multiplied together, and the dt and the dt get multiplied together, and that's why it's dt squared and d squared, okay? And this is our acceleration. It's acceleration. A of t is equal to v prime of t, which is the same thing as s double prime of t. This is the same thing as s prime of t, okay? All right, great. That's too much review. Again, it's fine. So what happens? So let's look at example one. Example one, the ball is dropped. That's important. From a height of 64 feet, also important. They give us a function for the height. So the function for the height is this negative 16t squared plus 64. So do you guys know what this graph looks like? If you took the basic graph of t squared looks like this. If you multiply it by 16, that makes it narrower. So it kind of becomes more like this, still like a U, like this. And then when you multiply by negative, it flips it like this. So this is a very narrow parabola opening downwards. And then when you look at that 64 shifts it up 64 units. So if you were to look at a graph of this guy, the graph would look something like this. Where this is 64. Yeah. Now, what I want you to see here is this axis, this x-axis is time, and this y-axis is feet. It's the height of the object. So we're not really allowing negative time over here. So it's like you drop the object, and then the y value tells you where the object is. So one thing I want to emphasize is this object is moving in a straight line. It's not moving in a curve like the parabola. The parabola only tells you what the height is going to be at different times. I hope that makes sense. So you're not throwing the ball into the air. The ball isn't making an arc and coming down. You're just dropping the ball and it goes straight down. It's vertical. It's only moving in one line. The shape of the curve tells us the position, but it doesn't describe the trajectory. Like sometimes students mess that up. So we want to know the instantaneous velocity. When you see the word instantaneous velocity, you got to think derivative of the ball when it hits the ground. So you have to do a sub-problem first, which is you have to figure out when the ball hit the ground. And when does the ball hit the ground? That's a position thing. Hitting the ground means the position is 0. So we're going to set this position function equal to 0, and then we solve it. When we solve it, we get plus or minus 2. So the reason why I'm explaining this graph here is that plus or minus 2 means this point here is 2, and this point here is negative 2. I hope that makes sense. That's when the ball is 0 feet above the ground, right? We're going to just take the positive 2 because that's the we don't allow negative time. And then once we have that 2 seconds, we just plug that into our velocity function. Okay, so what I want to talk about next is I want to do part B. So what's part B about? Average velocity. So when you guys see this word average velocity, is there anything that you think of? Like you wouldn't think of slope of a tangent line because that's instantaneous velocity. So what do you think of when you see average velocity? Any thoughts? Not slope of the tangent line, but slope of the. Nothing. Okay. When I see average velocity, I immediately think slope of the secant line. So this takes us all the way back to week 1. Remember week 1, I was talking about, or week 2, I was talking about secant lines and the slope of the secant lines, the limit of the slope of the secant lines gives you the slope of the tangent line. So that's what we're really trying to do over here. So I don't see a secant line, but this says what's the average velocity during its fall. So the start of the fall is up here and the end of the fall is down here. So to me, they're looking for me to find the slope of this particular secant line right there, that blue line. And what was part A about? Part A was about finding the slope of the tangent line at 2. So part A was kind of finding this. That didn't work out well. It's trying to find out this tangent line there. That looks too vertical. It's not that vertical, but it's pretty steep. Sorry, I can't live with that. That's too ugly. That's a little bit better. So you can see the purple line is a little bit steeper than the blue line because it's the instantaneous velocity versus the average velocity. So when we want to find the slope of this secant line, we're going to need 2 points. Anyone know what the 2 points I want to use are? You can type your answer in the chat box if you have a feeling. I agree, the starting point and the bottom point. So I have a question for you guys. Do you think that 64, 0 and 2, 0 would be the 2 points that I want or not? Oh, 0, 64, okay. Right, the 0, 64, that's the point right when they drop the ball. And the 2, 0, that's the point where the ball hits the ground. So this whole time is this whole part of the arc here, that's when our ball is dropping. So then the average velocity is equal to the difference in the y values over the difference in the x values. And that's going to be 64 minus 0 over 0 minus 2, which is going to give us negative 32 feet per second. Did we say it was feet in seconds? We did. I want to discuss for a second the fact that this is negative. Does that mean anything to you? Like, what's the deal with this guy being negative? Any thoughts? What do you think that negative velocity means? I think that means the ball is going down. In other words, its height is decreasing. I hope that's obvious. Okay. Any questions about this? No.